Okay, so let us open up the project, open the project, open a project, and let's just make sure that we are in the right directory. QPF is the project file, Quartus project file. Okay, so just open it, and at the beginning, it won't contain your files, so you need to add them. So to show the files contain the project, it's only the synopsis design constraint file that is there that defines the clock and the uncertainty and whatnot. Okay. طيب. So now I need to go and say add, and yeah. So this is, I need to add this, and this. I don't need to add the test bench. Okay, the test bench is only for simulation. Okay. Why? They are added now. So let's see what the top contains. Now I need to make sure that this is my top level entity, which is the Verilog file generated by the system builder. Okay, the system builder. So let's change this to top as well, because I have a module called square root. So we have these clocks available to us. Okay. Clock 50 is clock 50. So we have 4 of them, actually. All of them are 50 megahertz. These are the clocks on the FPGA side. And these are hex displays. And these are the keys, push buttons, actually. We have 4 of them. And we have 10 LEDs, okay, red LEDs, and 10 switches, okay? All right. So now I can actually use this, for example, if you have a register or wire declaration, you put it here, and here you have structural coding, okay? You don't have to follow this, but it's a good practice to do that, okay? So now I will create the filtered version of one of the switches to use it as my go, all right? So, but I need, for that, I need to declare or instantiate the debounce signal, okay? Debounce module, okay? I'm going to copy this. Of it here, and so for the clock, so this is debounce, and then let's call it 0, okay? And then for the clock, I have clock 50, which is this one. I just copied this, all right? And for reset, I'm going to use, this is, since it is an active low, I can use one of the keys, one of the push buttons. I'm going to use key 0 for that. Okay, this is the reset. My reset is going to be key 0. So whenever I have a reset, a connection to reset, I use key 0. Now the switch in is going to be one of the slider switches, which is SW. And let's use switch number 0. My switch out is going to be I go, basically. Okay. And I can say here, and just for clarity, I can declare I go as a wire. Okay. I don't need this, but it's just for clarity. So now my wire go is a clean signal that doesn't have any bounce. Okay. Any bounce. I actually don't need any of these. Okay. The next thing is I need to calculate this or instantiate the square root module. Okay, so I can go here and copy this. And this is my square root. Right, parameter scale. Let's say 16. Okay, parameter is 16. And you know what? I mean, it's difficult to display this on what we call on the LEDs if we have a 32-bit number. So we only have 10 LEDs, okay? So we are going to compromise the width and the scale, okay? So we are going to have only 4-bit for the scale, okay? And 8-bit, or let's say because we have 10 LEDs, let's say 10-bit for the whole number, okay? So this is a very low accuracy, and then I have to give it an instance name, yeah, instance name, and then I can just copy this. You guys are following?
Yes.
P0 for reset, and for data in, okay, for data in, I can use because I used already switch 0 for the positive edge. Yeah, I can use switch from 9 to 1. Yeah, that's what? That's 9-bit, not 10-bit. Yeah, 9-bit, not 10-bit. So I can actually say 1-bit 0, comma, these switches. Okay, so the most significant bit will always be a 0 in this case. And go is my, synchronizer. D out is going to be LIDAR, yeah, LIDAR, which is the red LEDs. Okay, I'm going to display my output in the LIDAR. I need something for ready. You know what? Let's just use 9 here. 9. And I don't need this anymore. It's already 9. Okay, I'm going to use 9 to 1, okay, for the LEDs, and then LIDAR 0 for ready, okay, for ready. No need for that, okay, no need for all of this. Right. Okay, so all of this now is prepared now. Okay, I'm going to compile this one. So just do not forget to set the top level entity. Okay. And I forgot to import the assignments. Okay. Import assignments. So there is import assignments here. Okay. And then I don't need to copy because I don't have any previous assignments. So this is QSF is my assignments. Okay. Click OK. Can't import assignments. And that. QSF. Let me pause the video and check what is wrong. So it turned out that I didn't need to import the assignments because they were the assignment file was having the same name as the project, so it was imported automatically. So now I'm going to compile, and this will take some time. So I'm going to pause the video and then come back when it's done. So we have finished compiling, and it turns out that we have 0 errors. Of course, we got some errors at the beginning. I corrected them. Quickly. Okay, so let me just give you the. Yeah, it was about almost in this line. Okay, it was syntax related there. Okay. All right, so now we finished that. Now we know we need to do what? Timing analysis, yeah? Timing analysis. Where is the timing analyzer? Yeah, here. And then clocks. Again, I'm doing that here, okay? And turned out that from the timing analysis, clock 50 is not enough for our circuit to operate at. Okay, our circuit is actually slower than 50 megahertz. So we need to run at a lower speed. Okay, you can see that here we have a negative slack, which means that there is a timing violation if you run at 50 megahertz. And this is expected actually because we're using, combinational division and then averaging addition, okay, at the same clock cycle. So this requires a lot of delay, okay, combination of delay. So our purpose now is not to boost the performance, but to remove this violation, okay? For this, I'm going to close timing analyzer and go back to Quartus. And then here in clock 50, I'm going to right click and then edit clock constraint in the timing analyzer, okay? I need to make sure that this is no longer 20, but it's the 20 plus the slack that we need, which was below 5 nanoseconds. So I'm going to add 25 nanoseconds, okay? And I want a duty cycle of 50%. I don't want it to be asymmetric, okay? Once you do that, clock 50 will be dealt with as actually a clock having a 25 nanosecond period, okay? Now, once we do that, we have to save the SDC file. Can overwrite it. Okay, overwrite the current SDC file. All right, and then close. We just overwrite. No need for writing the SDC file again. So say no here. We actually have, can see here, check the file. You can see that clock 50, okay, is having 25 megahertz. Of course, the board, clock 50, is having 20 megahertz, but I mean nanoseconds, but we will fix that later, okay, using PLLs. Right now, we want to make sure that timing is correct, okay? Timing is correct. So we need to now alert the IDE that we changed something so that we can recompile. Okay, I just added a space here and then saved. So the Quartus detected that, and we have to recompile in order to get the latest bit stream. Okay, so now we will recompile and then check the timing analysis again. I will pause the video because this takes a little bit of time, and then come back when it's finished. Well, compilation is finished. We can see that timing analysis here is actually also finished. So now we want to report timing, okay? Report timing and see if we have positive slack or negative slack as before. I'll start from clock 50 and end at clock 50 and examine all the paths in between. Luckily, we have a green slack here, meaning that the slack is positive, okay? So 25 nanosecond is enough. I can close the timing analyzer now. And then in the next video, I will talk about how you can generate a 25 megahertz clock. 25 nanoseconds period clock, which is 40 megahertz clock, using PLL, okay, a PLL component. I'm going to stop recording now and continue in the next video.